All right, welcome everybody. Good afternoon. Another beautiful day in Math 161 on the internet. All right, so I just wanted to point out that our test 2 dates are, I'm going to be coming up with that by the next class. We're still, figuring things out one day at a time. So I think I've mentioned before that test 2 will work very, very similar to the last one, and that I will have a review available for you, as well as a test in my math lab with 2 attempts. So you want to make sure, and you'll have a range of dates. It's not just going to be a single day. I'll give you probably 3 days to complete the test. You'll get the review at least a few days before the test goes live to make sure that you've got time to focus. And there was something else I wanted to say about that, but I want to hold on until next class. I don't want to implicate myself. There's something I want to do, but I don't want to say just yet. All right, so we're going to pick up where we left off last time in 2.3, which we had done example 4, A through C, for the average rate of change. So we had done A, B, and C, and there's going to be a D that is not listed up here. And that's going to be f of x equals x squared, and we're going to go from -3 to 3. But I would like to remind us what that formula is. And remember, if you don't catch a lecture, the links are in Canvas to take you to YouTube. All right, so our average rate of change formula is going to be f of x2 minus f of x1 all divided by x2 minus x1. And we said that this was calculating the slope between 2 points on a function, the average slope. On a graph. And let me kind of give you a visual representation of what that means. So here's a random curve. And let's say we had point 1 here, and then point 2 here. So we'll call this P1, which stands for point 1, and we'll call this point 2, P2, which stands for point 2. So the average rate of change from x1 to x2, and it doesn't matter where these are, but the graphic representation of this is a tangent line, secant line. Tangent line means touch and go. It's only a single point. Secant line uses 2 points. So it's a secant line between those 2 points, as straight as possible. I got my drawing tablet, so I'm not too perfect with it. But the slope of this line is the average rate of change between point 1 to point 2. So the average slope of this graph between these 2 points would be the equivalent slope of a secant line if you drew a secant line between those 2 points, connecting and extending them. That's what average rate of change relates to. All right. Where's my mouse? There we go. So let's do example 4D. Let me switch back to black. And we're going to have the function, as I said earlier, just a basic x squared. And we're going to go from x1 being -3 and x2 being +3. So we're trying to find the average rate of change, the average slope of this function from x values of -3 to +3. Well, we need the y values, also known as the function values, so we have to plug in these -3 and +3. So f of x1 would be f of -3, which is -3 squared, just plugging it into the x, and that's positive 9. So f of x1 is positive 9. F of x2, that's the f of positive 3, which would be positive 3 squared, which is also 9. So the outputs for the first and second points are identical, and we haven't seen that happen yet in the previous 3 examples. It doesn't necessarily mean anything super important. It's just kind of a special case. That's all it really is. So our average rate of change, using the formula that we are supposed to memorize from the previous page, f of x2 minus f of x1 is 9 minus 9. They're the same numbers, 9 minus 9. Over x2 minus x1, that's 3 minus negative 3, which is 9 minus 9 over 3 plus 3, which is 0 over 6, which is 0. So that says that the average slope from negative 3 to positive 3 of the function x squared is equal to 0. Now, we haven't seen an average rate of change that was 0 in the previous examples. I'm not saying that other examples don't exist. I'm just saying we hadn't seen one together. I'm kind of curious as to, the picture of this myself, going back to what we just saw on the last screen. So let's draw this up. Doing my best. Doing my best. It's a little steep, but that's okay. That side's a little better. It shouldn't be this flat right here on the right side is all I'm saying. The left side looks a little better, but this will demonstrate the point. So we got 2 points that we found over here at negative 3, an x value of negative 3. We had a height of positive 9. So this height is 9. And then at an x value of positive 3, we also had a height of 9. So these were the 2 points of which we just found the slope between. And if you connect those with a line, I'm going to do it as a solid line this time because making dotted lines on this is extremely difficult. So here is the secant line, the line that connects the 2 points that we're trying to find the average rate of change from. And guess what the slope of a horizontal line is? Shouldn't be a guessing game. We talked about this last time. It's 0. And that agrees with the average rate of change that we just calculated. So if we had done this, say, from 0 to 3, the line would have looked like this, if you can see my marker kind of moving in a positive slope manner. And that would have been a very different average slope, a very different average rate of change. So it's extremely dependent on the 2 points of the function. Now, this black curve was the function itself, x squared. And this is a shape that I feel like you should already have seen multiple times throughout math, but we absolutely have to have this memorized in the next section, as well as several others, as we will see in just a few minutes. All right, so that will close out section 4 of chapter 2. That ends section 4 of chapter 2. So that means we can move on to section 5. And I'm just going to go ahead and leave this on a whiteboard for now. So 2.5. Transformations of functions. 2.5 is on transformations of functions. We are really going to start diving in to more advanced graphing from here on out. A lot of the things that we're going to focus on for the rest of the semester are about graphs of polynomials, graphs of rational functions, graphs of exponential and logarithmic functions, assuming that we can get that far. So to start this out, what we have to do is memorize a few basic shapes. You're going to have to memorize a few basic shapes. And the first one is one we just dealt with, f of x equals x squared. Give me the drawing. There we go. F of x equals x squared. This graph goes through the origin, and then it looks like a U. So we kind of start growing quicker and quicker and quicker as we move on. Like so. This is our parabola. This is our quadratic shape. Now, not all graphs start at the origin and move up. Sometimes these things will be pointing down. Sometimes this point right here, which is known as a vertex, as we'll talk about moving forward, this vertex can be anywhere. It doesn't have to be on the origin, and that's going to depend on whether there's extra numbers with this x squared. Maybe there's a +5 here, or there's a parentheses x minus 2 squared. That would change things around. But this U-like shape is the basic shape we're going to have to start with in terms of memorization. Next up, we have our x to the third power. And it's going to look kind of similar to the x squared, kind of similar. The right side looks extremely similar, except it grows a little quicker than the other one. It's just growing a little quicker. It starts getting higher up on the y-axis, a little quicker than an x squared. But the left side does not point up. The reason the left side of x squared points up is because this always makes outputs positive. So if you plug in negatives, you get positives, just like in the last example we saw when we plugged in -3. But when you plug it into a negative into a cubic, it stays negative, which says this shape stays on the bottom half. So it's got that same type of curvature, but it points down instead. And again, that's because plugging in negative x values will lead to negative y values for x cubed, whereas for x squared, plugging in negative x values turns into positive y values. Now again, between x squared and x cubed, as you move further and further along, x cubes are supposed to grow a little quicker. It points up a little more. This is not something that I would be grading harshly if this was a pencil paper test, which obviously we're not taking. But it is important to understand that conceptually. All right, f of x equals, let's do the absolute value of x. And we've talked about this shape before. We've seen it in a homework problem or two, as we have with the other examples. An absolute value of x actually has more in common with x squared than you might think, because when you plug in a negative into an absolute value, it always becomes positive. So there's no way that this output can be negative. Now, an absolute value of x just means that it's linear, but it's going to change at the origin. On the right side, that line is moving up and right with a slope of 1. So the slope of this line is 1 because there's an imaginary little 1 or an implied 1 here. And no, it's not the 1 that's the absolute value. That's not a 1. But on the left side, when we plug in our negative x values, they're going to turn positive because of the absolute value. Now, if we were just graphing x, it would continue down here. But we're flipping this thing upside down, kind of like we did with the x squared, and it makes it look like a v. And the slope on this side is -1. So the slope of the left half is -1, the slope of the right half is +1. This actually looks like a piecewise defined function. In fact, the literal definition of an absolute value is set up as a piecewise defined function because you have this drastic change, kind of a turn on a dime right here. But again, both ends point up. It's not taking place in any of the negative things. You'd need extra negatives in this function for that to happen. All right, let's go to the next page so I can keep my space available. Next up, we have our square roots. So that's our square root of x. And this graph kind of looks like you took the x squared and tipped it on its side. So something like this. Again, it looks like you took the x squared and tipped it on its side, and I'm going to pull out the red for just a second. If I did the whole x squared on its side, this is what the image would look like. But guess what? This fails the vertical line test. So this is not a function, which is why we have to cut off that red portion. We have to cut off the bottom leg, if you will. I know that sounds brutal. In order to make this a function. So this is the square root of x. It starts again at the origin, and it's got, instead of really quick growth, we call this slow growth because it's kind of flat, kind of like what we want to see COVID-19 growth curve turn into eventually. Right now, we're in a quick growth part. All right, next up, we got our cube root of x. And this one's going to look very similar to the square root. It's going to be a little slower in terms of growth than the square root, but it also will look like this on the left side. So it's kind of like the x cubed. It looks like the x cubed tipped on its side, in fact. But when you tip the x cubed on its side, that doesn't fail the vertical line test. So that's why square root of x and cube root of x are very different. And it has to do with the even or oddness of the index. Even indices always end up having this, quote, chopping a leg or arm off section, whereas the odd ones do not. I'll admit we don't use graphs of cube root of x a whole lot in here, but it's still good to see it, of course. And then the last two that I'm going to do, I feel like are really unnecessary, but I'll write them anyways. F of x is equal to c. That means c is a constant. That's just a number. This graph is a horizontal line. We talked about the graphs of horizontal lines last time, and that height right there would be c. And also the graph of f of x equals x is just that's a little quick, is a line with a slope of 1. It goes through the origin. Because it has no y-intercept, this is in slope-intercept format, which we've discussed in the last class, the mx plus b. So the m is 1. There's no plus b, so that's why it's sitting at a height of 0. Now, the reason I have asterisks is next to these, it's not because they're more advanced or special, it's because, honestly, we're not going to use them for anything having to do with this section or moving forward. If you're asked to graph a line like 2x plus 3, just graph it like we did in the last section. Don't use transformations because you're going to make the problem much more complicated, in fact. Same thing for f of x equals 5, or f of x equals -10, or f of x equals 7. Just remember that that's a horizontal line with that specific height. Doing transformations is going to make this problem much more complicated. So again, I am suggesting that you memorize the shapes of square root of x, cube root of x. I even admitted that one's not used as much, but you'll see it. X squared, x cubed, and the absolute value of x. So that's 5 that I'm suggesting that you memorize out of the 7 that I've really just given you. So with those shapes memorized, we can then, sorry, I have to move something. Nope, wrong thing, 2.5, here we go. So here, got some type notes already set up for this section. Basic graphs to memorize, C board, that was the whiteboard that we just did. Let's talk about vertical shifts and horizontal shifts. So the idea of this section is that we're going to just paint that original picture. If we got a graph that has an x squared in it, then we're going to graph that u shape. If we have an absolute value somewhere, then we're going to graph that v shape. If we have a x cubed, then we're going to graph the shape that has it going up on the right and down on the left, and it bends kind of like a parabola. So for a function with a known graph from before being the things on that whiteboard, the transformations of the following shift. Shift means to move up, down, left, or right. So we're focusing on vertical shifts for now. So that means up and down. And we said that we're going to use the letter C to represent a constant. It doesn't have to be a whole number. It can be fractions or decimals, but they're usually whole numbers. So if you see a chunk of a function that you know what the graph is. So if you have, let's say this was an x squared plus a c, you know it would look like that U shape, but you're going to take the U shape and you're going to move it up by however much that number is. That kind of makes it feel like a y-intercept. In fact, it is exactly a y-intercept. Or if it's minus that number, then that means you're going to shift it c units down. And again, c just means whatever that number is. So let's just focus on the vertical shifts for now. I know the horizontal shift stuff is up here, but let's focus on the vertical and do a couple examples with that. So just the vertical. So if you see plus a number, you're moving the shape up. If you see minus a number, you're moving the shape down. Okay. Wrong thing. Whiteboard. So example 1A. Well, example 1, the instructions will be, and I like to say this a little loosely, some people will say graph, I like to say sketch. I like to say sketch because we're doing this with a one-point method. We are only going to be moving that point that started at the origin and then just draw the basic shape from that. So you move the origin point based on the transformation. Then sketch the basic shape after that. So for A, we got f of x is equal to x squared plus 3. F of x equals x squared plus 3. So this is exactly what we were just talking about. We have what I like to call the core function, but then we're either adding or subtracting a number. In this case, we're adding. So we have our core function, which was an x squared, and we're going to shift it c units up. So because of this plus 3, that says to shift this up 3 units. So let's do blue. I'll do the basic x squared graph. This is not the solution. This is not the solution. This is not the solution. Again, blue, that's f of x equals x squared. In red, I will do the graph where it's shifted up 3 units. So 1, 2, 3. So there's our height of 3. All we did is we took the point that was at the origin, we move it up 1, 2, 3 times, and then we draw our parabola shape from there. And again, bear with me with my drawing tablet. So this red curve is the actual answer. That's x squared plus 3. Now in class, I would normally do these as dotted for the old ones, but it is extremely difficult for me to make a picture pretty with dotted curves on this tablet. So again, the red is the answer here. The blue was just used to get there. Do you have to do that first? Some students say no, some say yes. It depends on what you feel comfortable with. So please do what you feel comfortable with. Some people will only have the red. Some people I'll see the starting image and they'll show the transformation. B. Let's go with f of x equals, how about the square root of x minus 5? So again, the square root of x here is what I would call the core function. Is there a benefit to doing both? I would say yes, when there is a lot more going on. So we're going to get to some examples where we have to move up and then right and then flip things around. So in those instances, I find that drawing these ghost images, the previous ones, I find it to be helpful. And I think that a lot of people would agree with me. But if it's just one transformation, just moving it up or just moving it down, you probably would feel fine without doing that. All right, so square root of x minus 5. So this minus 5 is the transformation, the thing that makes it move to somewhere else. Because that's a minus, that says it would go down 5 units. So we're going to take the core function, which is the square root of x, which was that parabola on its side with half of it missing, and that's pretty detailed, and we're going to shift it down 5 units. Oh, that was bad. Let's try that again. Good enough. So your basic function, again, I'm using blue for the ghost image. So this is not the answer. This is just what I'm using, and then I'm going to transform it. So this would be the square root of x. But we need to take this thing and move it down 5 units. So red will be our answer. 1, 2, 3, 4, 5. So here's a height of -5. That point that used to be at the origin is now sitting here. And then we just draw the exact same shape, but stemming from this point down here. So it's not going to go up really quick. It's going to go up just as quick as before. So that would be the square root of x minus 5. So that's vertical shifting, vertical transformations. When you have a plus or a minus number, and I say this very specifically, outside the core, the core being the x squared and the square root of x in these problems. So when the number, the plus or minus number is outside the core, that makes it shift up or down, outside the core. What if it was inside? So let's see what happens if it's inside. Let's go back to our notes. There we go. So now we're at the horizontal shifts. So for a function with a known graph from before, in other words, we know a core, a square root, or an x cubed, or an x squared, or an absolute value, any of those 5/7. Horizontal shifts are seen in this format. Instead of the plus or minus number being outside the core, and I'm not saying they're to the right because these numbers can actually be in front of the core. It's just that they're outside and not inside. How can you tell whether outside or inside? Because it feels like that number is going to be inside of a parentheses or inside of something else. So that's what this is trying to demonstrate here, where the plus c or the minus c are inside with the x instead of outside. Now you'll also notice something that feels a little weird at first. The shift to the left is actually when it's positive, so a plus and then a number, and a shift to the right is actually when it's negative. These feel reversed. This is something that you have to practice. If you just think you're going to say this or write this or do this once and then have it aced on a test, you're probably wrong, unless that's how your brain works, which is rare. I had to practice this many times to get it right, so will you most likely. So the vertical shifts are not backwards. Plus is up, minus is down, but the horizontal shifts are backwards. Plus is left, minus is right. And there are reasons for this, and it can be demonstrated by actually plugging in the point that we're shifting around to make sure that the math lines up. But I don't want to get into too heavy of the details for that. We save that for later in pre-calc 2 or calc 1. But again, the point I was emphasizing earlier, horizontal changes are always inside, what I call the core, where vertical changes are always outside. And this is going to be true for everything in this section. Horizontal changes are inside, vertical changes are outside, because we're going to see reflections after this, and that line of logic stays the same for those. So that's actually a really helpful statement right there. So let's try this out. So again, vertical shift. Here's your x squared, then a plus 3 outside. Here's your square root of x, then a minus 5 outside. Those were vertical changes. Example 2. Draw graph sketch, and I don't want this to be red. Graph/sketch. A, we're going to do f of x equals absolute value of x plus 4, where the plus 4 is like that. Can you see what I mean by inside versus outside? Let's go back to example 1 for a hot second. This plus 3 and this minus 5 were away from the basic shape that we have memorized, square root of x, x squared. Then away from them is the plus 3 and the minus 5. With this example, I think I just hit a new screen. There we go. With this example, this plus 4 is not away from that. It's not over here outside of the absolute value. It is inside. So this is what symbolizes a horizontal shift. So because that's a plus 4, that does shift it 4, either left or right, but you have to remember that this is backwards. So the plus 4 will actually shift it left 4 units, not right 4 units. So here's that absolute value of v, absolute value of v, excuse me, absolute value of x that is a V shape. And again, I would normally do that dotted. So that's just the absolute value of x. But we're supposed to move this thing left 4 units. So we'll go left 1, 2, 3, 4. So here's -4. That point at the origin is now sitting at -4 on the x-axis. And then we draw our v from there. So the blue one is the absolute value of x with the plus 4 inside. The blue is the answer here. So again, the blue here is the answer. The red, you do not have to draw. However, if this was a paper pencil test, I would say that's how people can get partial credit. Maybe you moved it 4 right instead. By showing the ghost image, I could at least give you a point or two saying, all right, well, you know what the core is supposed to look like. You did part of it right. But you're going to end up with a multiple choice test for this type of question. The whole thing is not going to be multiple choice, but for the graphs, I have to give multiple choice questions with this internet version. Pros and cons. Just because it's multiple choice doesn't make it easy. Please don't think that. And again, the whole thing is not going to be multiple choice, just a few questions. B, f of x is equal, let's do parentheses, x minus 2 to the 3rd power. So it's the minus 2 that does the transformation. And that minus 2, does it feel like it's inside or outside? Pause for answer. And then someone says it's inside, right? All right, so this minus 2 is inside, which means it's a horizontal shift. It's either left or right. Because it's a minus and the horizontal shifts are backwards, this is actually right 2 units. Okay, so let's go ahead and make our graph. Let's think about what the core of this should look like. Well, I see an x and a 3 is an exponent, so that's an x cubed, which means that the core, the original function, has this basic shape. That's our x cubed. That's the basic shape with no extra plus or minus numbers anywhere. And then we're just going to transform this by shifting it right twice. 1, 2. So here's an x value of 2. There's our new point that used to be at the origin. It's just moved right twice. And again, the red curve is a ghost image. That's not actually part of the answer. Just the blue is the answer. So that is our x minus 2 in parentheses cubed. Same as the other example, blue is the answer. Okay. So one last quick look at these two examples. When the number's outside the core, that's a vertical shift. And again, I can have the 3 in front of the x squared. I can have this minus 5 in front of the square root of x and then write a plus square root of x after it. It doesn't have to be at the far right of it. It's just outside of the thing that's really dictating how this function is going to be moving. So this is what it looks like when they're outside in their vertical shifts. This is what it looks like when they're inside, which causes horizontal shifts. And spoilers, we will see examples later that have both. But for now, let's talk about reflections. Reflecting on reflections. So the graph of negative f of x is a reflection about the x-axis, also known as a vertical reflection. The graph of f of negative x is a reflection about the y-axis. This is a horizontal reflection. I'm going to highlight this important statement I mentioned earlier. All horizontal changes occur inside, and all vertical changes occur outside. That is really going to help you remember how to do the reflections. So a vertical reflection means everything that was on the top goes to the bottom, everything that was on the bottom goes to the top. A horizontal reflection means everything from the left goes to the right, everything from the right goes to the left. We talked about this idea with symmetry previously, but now it's not necessarily that we're using symmetry, we're just using a reflection and it kind of feels like symmetry. But it's not symmetry because the original image is part of another function, a simpler function. So vertical reflection, vertical things happen outside. Look at this negative. It is outside of the core f of x, that core x squared or x cubed or square root of x, whatever function. This negative is outside, whereas this negative here I wish that was a different color, but oh well. That negative is outside, whereas this negative right here, that one's inside. So when you have a negative in front of the x term inside, that makes it a horizontal reflection. Left and right will swap. When you have a basic core function and there's a negative in front of that core, that means you're going to reflect outside. I'm sorry, you're going to reflect vertically because the negative's outside. Excuse me. A negative in front of an x inside flips left and right. A negative outside the core flips up and down. Okay. Example 3. Same instructions, graph, sketch. And this is going to be f of x equals negative x cubed. So the core function is the x cubed, so it looks like it growth on the right and it goes down on the left. It looks like that parabola, but you take its left arm and you point it down instead of up. But there's this negative outside. This negative is outside the core, which makes it a, that's right, vertical reflection. Might be the straightest axes I've drawn today. So we'll do blue for the original this time. So here's our ghost image. Again, this blue is not the answer. This is just something I'm using for constructive purposes. And it's a little steep, but that's okay. So this is our basic x cubed graph that we're supposed to have memorized. But we are supposed to reflect this thing vertically. Vertically means up becomes down, down becomes up. And I'm going to draw a red line. I'm going to do a red dotted line to represent the mirror. So our mirror is the x-axis to make up become down and down become up. So this section on the right-hand side that was originally going up and it's going up quicker and quicker and quicker, we're just going to mirror that across that dotted vertical line to look like that. So again, this red portion right here is an image of a reflection of the upper right portion. So that was me flipping just the right-hand side. I haven't done the left yet. The left-hand side, the blue image was originally pointing down, and it's pointing down, 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 even further as you move left. So now we're going to take that and point it up. Down becomes up becomes down. So something like this. So the red image is the answer. That's our negative x cubed graph. So again, just the red on this page is the answer. The blue image is a ghost image. This is not two parabolas with different colors on each side. The blue section is one curve. That was the regular old x cubed. The red one is the negative x cubed, which was a reflection vertically. And again, if you don't like this being on the same bit, you can just somewhere else go really quickly, redraw your answer. There we go, pointing down and pointing up. There's our answer. You can always redo everything without the ghost images. And that was 3A. I forgot to write A. B. F of x equals the square root of negative x. So the core function here is a square root of x. It looks like the parabola tilted on its side, but with one of the arms missing. But there is a negative in front of the x inside. It's not just that there's a minus a number somewhere. That's a shift. Having a negative in front of the core or in front of the x inside, that's a reflection. So this negative in front of the x causes a reflection. Since that's inside, it has to be a horizontal reflection. All inside changes are horizontal. All outside changes are vertical. So we're doing blue for the ghost image, not that blue. Oh, I gotta draw the axes first. So again, we're gonna do blue for the ghost image. So a regular old square root of x looks something like that. That's our ghost image. That is not part of the answer. We're just using that to get the answer. But we're going to reflect this horizontally, which means left becomes right and right becomes left. So the y-axis is what we're reflecting across. Again, I'm using a dotted line here to show my mirror. So everything that was right now points left, everything that was left now points right. Well, there was nothing that pointed left before, which means there'll be nothing pointing right before. But all this stuff that was pointing up and right is now going to point up and left. Sorry, it got a little rigid there. That's a little better. Good enough. That's the square root of negative x. Once again, the red is the answer. The blue is a ghost image. If you wanted to avoid confusion, you can then just go somewhere else and just do that one by itself. Say that's the answer. Every change inside is horizontal, every change outside is vertical. That's probably the 10th time I've said that now. That is the best thing to go off of, along with the fact that the horizontal changes feel backwards. Vertical changes, up is positive, down is negative. Horizontal, positive is left, negative is right. Let's do one more of these with the reflections. C. f of x equals negative square root of negative x. Negative square root of negative x. Well, guess what? This has a negative inside. So that's a horizontal reflection. I'm abbreviating now, and I'm going to do that a lot moving forward. HR for horizontal reflection. Make sure you understand that. But then this negative here has a yellow look on the screen. Is that okay? Vertical reflection. Because this negative, the yellow one is outside, that's a vertical reflection. The one I have in green is inside, so that's a horizontal reflection. So in other words, this is going to reflect both ways. Now, I will say for this problem, the order that we do this doesn't matter. And in general, the order that we do these two reflections doesn't matter. However, when we get to the next examples where we have all sorts of reflections and shifting, the order that things are done in will actually start to matter. And I will explain the necessary orders and kind of give reasoning for it. All right, so we're going to need two different ghost images this time. And again, for now, when it's just two reflections, the order doesn't matter, but ultimately this can matter. So in blue, I'll do the original square root of x. Again, ghost image. This is the basic core function that we have memorized. Someone said they're having volume issues. I'd say probably turn up your volume. You can do that on your computer in the lower right screen, like next to your the date and time and everything. If you click the speaker, maybe you can make that louder. I haven't heard anyone else say that volume's been an issue for me. If anyone else is having that issue, please say. I'll try and speak a little louder otherwise. All right, so back to the problem, square root of x, that was our basic core. Let's do the horizontal reflection first. So we'll do, let's go with purple for the horizontal reflection, which will make right and left change. So this graph now looks something like that. So it's pointing up and left instead of up and right. So this right here is just the square root of negative x. So that's the horizontal reflection. Now we're going to take this purple image. This blue thing is gone. Now we're dealing with the purple image. And we're going to reflect it vertically. So we're only reflecting the purple, not the blue, just the purple. So everything that's up becomes down, everything that's down becomes up. So this will now point like so. Doing my best. This right here would be negative square root of negative x, which is the answer. Again, the red is all you actually have to need for an answer. So if you wanted to just draw it by itself, something like that. It should have been a little flatter throughout here, but that's okay. That's good enough. Like I said, you're not really going to be doing a lot of this stuff by hand for tests or homework. You just have to be able to pick out the correct looking graph. So we saw a problem with a vertical reflection, we saw a problem with a horizontal reflection, and we saw one that did both. We saw problems that had vertical shifts, we saw problems that had horizontal shifts. Now what we want to do is get a big old mixing pot, throw everything into it, stir it up, and see what happens. So now we're going to start throwing everything together in one example. So I mentioned previously that when you start mixing a whole bunch of different ideas, the order that you do them will actually matter. You can end up with incorrect graphs by shifting and reflecting in an improper order. And the crummy thing is that the order is backwards from horizontal versus vertical, and it probably has something to do with the fact that horizontal shifts are backwards. So You must do horizontal shifts before reflections. You must do vertical shifts after reflections. So again, this is kind of weird. Horizontal shifts have to be done before you go reflecting horizontally, but vertical shifts have to be done after you do the reflection. So while this down here is not the ultimate only order to do things properly, it is the order that I suggest things to be done in. So what I like to do is knock out all the horizontal stuff first, anything that's H is horizontal. So I'll do the horizontal shift, then the horizontal reflection. If you do them backwards, your answer will be wrong. I can guarantee that. You have to do the horizontal shift, then the horizontal reflection. Then I do the vertical stuff. So I do all the horizontal, then I do all the vertical. And this order is backwards here. You have to do the vertical reflections before the vertical shifts. So I'm doing my shifts first and last, the reflections in between, and you have to do the horizontal shift first. You could actually do the vertical stuff before the horizontal. You can do the vertical reflection, then the vertical shift, then the horizontal shift, then the horizontal reflection. You can actually mix horizontal and vertical stuff. You could do horizontal shift, then vertical reflection, then horizontal reflection, then vertical shift. There's at least 4 different orders of things that will get you correct answers, but there are a lot more orders that will get you incorrect answers, which is why I'm kind of suggesting one particular method. Split it horizontally and vertically. Do horizontal stuff before vertical stuff. Do the shifts on the outsides. So first and last for the shifts. So I'm just going to add a little memo. Horizontals before verticals. Shifts should be first and last. That goes in line with what I do. I'll do all the horizontal stuff, then all the vertical stuff, and I'll make sure that the shifting is first and last. How do I know I'm not doing the vertical shift first? Because horizontal goes first. All right, that should be it. Okay, so let's try this out. So we're up to what, example 4? Yes. And we're still graphing slash sketching. And for A, we got f of x equals negative parentheses, x minus 4, close the parentheses, square it plus 2. So this has got a whole bunch of different things going on with it. We've got to make sure that we account for all of the 3 or 4 or 5 or 10 million things going on. And we have to make sure we get them done in the proper order. So we said, as a reminder, we should do the horizontal stuff first with the shifts first and last. So it's horizontal shift, then the horizontal reflection, then the vertical reflection, then the vertical shift. Again, not the only order it can be done, but the order I will always do things in. Is there a horizontal shift? Well, yes, there's a minus 4 inside, which is a horizontal shift. And horizontal shifts are backwards, so that's actually going to be right 4. That's a right arrow. So there's a horizontal shift of right 4. Is there a horizontal reflection? Well, that would be a negative inside. There is no negative in front of the x inside. And again, this minus is with the shift. I'm talking about a minus paired with the x, not the constant. So there is no, I'm writing none, for a horizontal reflection. Vertical reflection, well, there is a negative outside the core, which causes a vertical reflection. So we will reflect vertically. Up will become down, down will become up. And then is there a vertical shift? Well, that's a constant being added or subtracted outside the core. And there's a plus 2 here. So that says we're going to shift up 2. Remember, vertical shifts are not backwards. It's the horizontals that are backwards. So we got to take an original ghost image, and the core is the thing being squared. So x squared is the core. We're going to shift it right 4, then we're going to reflect it vertically, and then we're going to shift it up 2. And I might even show you what this would look like if we did it incorrectly. All right. So I'm going to need several ghost images. I'm going to try my best to do dotted. So x squared is the original ghost. Might be a little steep, but we're not going to focus on that. So this was x squared. We're then going to shift this thing right 4. Let's go with green. So we're going to go right 4. 1, 2, 3, 4. Let me do that in black. 1, 2, 3, 4. So now we just take this point that used to be sitting at the origin. We call that a vertex. And it's now going to be here. And then we draw our basic parabola from there. Again, I'll do my best for the dotted. I'm getting a little better. There we go. So this would be the right 4 graph. Specifically, that's x squared minus 4. Now let's do the vertical reflection. We'll do this with, how about orange? So the vertical reflection takes the green image, the blue's gone now. We're only focusing on the most recent ghost. So we take the green and we reflect it vertically. So up becomes down becomes up. That's still sitting on the axis. I drew it just a little lower so I'm not covering up the green point. So this would be negative parentheses x squared minus 4. And then we do the vertical shift. The vertical shift is the up 2. So we're only going to take the orange image and we're going to move everything up 2, and this will be our answer, and we'll do that in red. So this will be solid. So up 2, 1, 2. Here's a height of 2. So this point goes up to a height of 2, which is right here. And the orange image was pointing down, so this red image should still be pointing down, but now it's solid. Because this is our answer. This is how I really like to do things. So that would be the negative parentheses x minus 4 squared plus 2. Do you have to label these functions exactly as you go? No, I'm just being thorough. Now that red image is correct. This point right here is 4, 2, because we went right 4 up 2. That's kind of the apex of this quadratic. If you want to check these, what you can do plug in the vertex point. So we're doing f of 4, because that's the x value. That would be negative parentheses. The x value again was 4. So that's 4 minus 4 squared, then a plus 2. The inside 4 minus 4 is 0. Now, what you'll generally see is exactly that happen. You're going to end up with a 0 somewhere when you do this, if everything works out. So that's negative parentheses 0 squared plus 2, which is 0 plus 2, which is 2. So that point is 4, 2. That's a great sign that our image is correct. It doesn't guarantee that everything is drawn. It doesn't guarantee that we drew the appropriate shape. It doesn't guarantee that things are pointing up or down appropriately, but it does guarantee that we shifted and reflected appropriately. So what I'd like to do over here now, we're going to do this wrong now. So instead of shifting right 4, then a vertical reflection, then up 2, let's say we did the horizontal reflection, we got that right, then we didn't reflect horizontally, then we do the up 2, so right 4, up 2, and then we do the vertical reflection. So again, everything I'm doing over here on this bottom right section is wrong. I'm going to do it a little quicker. So we have our x squared graph originally. So that's x squared. We're then going to shift it right 4. I'll keep my color order the same. Well, no, I'm not actually. That's a lie. Right 4, right 1, 2, 3, 4. So that's right 4. And we're still pointing up. So that would be x minus 4 squared. Then I'm going to do this up 2. Things are getting a little squished, so I'm going to stop writing what this is. But that would be parentheses x minus 4, close it, and square it, and then adding the 2. And now I'm going to do the vertical reflection. So red will be the answer here. So the vertical reflection, oops, that was terrible. Means that the x-axis is the mirror. Now, the yellow or orange, whatever color you want to call that, that's what we're reflecting. Now, this point right here was at 4, 2. Now, I don't just turn around on that point. I don't just reflect it down. A vertical reflection means that the dotted line, the axis, is the mirror. So this point that was at 4, 2 ends up now having a height of -2, and then we point it down. And we can see that this is different than what we got before, because this point right here is 4, -2. And if you plug that into the function, we can already see that it doesn't match. We get the point 4, 2 by plugging it in, but we just drew the point at 4, -2. So this really shows you that the order does matter. If you do a vertical shift before a vertical reflection, this is exactly what happens. Your point ends up at the wrong height. If you do a horizontal reflection before a horizontal shift, the same thing happens, but in terms of left and right. So again, I cannot stress enough, and this is what people get wrong on tests. You have to do the horizontal shift before the horizontal reflection. You have to do the vertical reflection before the vertical shift. Everything else you can play around with. I just really like this particular order. That's my favorite. And again, if you don't trust your answers, plug in the x value, see if it spits out the y value, and that's a good indicator for whether you've done this right or wrong. All right, we're going to do 2 more of these for good practice. So B, graph, sketch, f of x equals the absolute value of -x plus 2, close the absolute value, then a -3. All right, so let's start identifying the important stuff. And as a reminder, we're going to do the horizontal shift first, then the horizontal reflection, then the vertical reflection, then the vertical shift. Is there a horizontal shift? Well, there's a plus or minus number inside, so yes, that's +2, which means we shift left 2. Is there a horizontal reflection? Why, yes, there is a negative in front of the x. Remember, horizontal stuff's inside, so we're attacking insides first, then outsides. The negative x means that there is a horizontal reflection. Is there a vertical reflection? Well, there's no negative outside the what I call core, which is the absolute value symbol. So there is no vertical reflection. Is there a vertical shift? Well, yes, there is a number being added or subtracted outside the core. And again, this -3 could be in front. That -3 says that there is a shift of down 3 units. So we've got 3 things to do to this one as well. Okay, just gonna do it here. I can do better than that. Much better. All right, so I'll do a black dotted line for the ghost image, the original ghost image, which is just an absolute value of x. So that's a V pointing up on both ends. Don't make it too flat. Don't make it too steep. Want that porridge just right. So that's the absolute value of x. And instead of writing what they're called here, I'll skip that this time, and I'll just do the images. So the first step, we have to shift left 2 before we do the horizontal reflection. Let's do that in blue. So left 2, here's 1, here's 2. So now that bottom of the V is sitting here, and it still points up on both ends. Try and make the slopes match from each ghost image for these absolute values. You don't want one V to have this shape and then the next one to be shaped like that. So let's say this was step 1. I'll just label in terms of step order. So that was the first step from the ghost image. The original one was an absolute value of x. Now let's switch to, let's go to orange. For the second step, that's the horizontal reflection. So left becomes right, right becomes left. Now you might think, oh, reflecting this horizontally doesn't do anything because our mirror is here, and it's not there. The mirror is the y-axis. Again, this is something that's very commonly mistaken. This is our mirror right here. So this point that's originally left 2, when you mirror image that, it's going to go right 2. Again, this point that was left 2, when you mirror it horizontally, will now be right 2. And then you just draw your V from there. So that was the end of the second step. For the third step, well, there is no vertical reflection, so we're not changing up and down, but we do have a vertical shift of down 3. So down 1, 2, 3 to a height of -3. And I'll do red, and this will be the final one. So this point, we're using the orange ghost image. We go down 3, which will put that point right there at 2, -3. And then we draw our V from there. Again, this thing is still pointing up. We never reflected vertically. So this is our answer, or step 3, if you will. And again, if you don't like having all this jumbled information on the same page, what you can then do with all of that is just go to the side and draw the point 2, 3, 2, -3, excuse me. And then draw your V from there. And there's your image. And that's all you're going to see in those multiple choice questions, homework quizzes, and tests. No, no quizzes, but homework and tests. If you were to give me all the ghost images, that's fine. If you redrew everything with just a single one, that's fine. I wouldn't really like seeing a student not have the middle work though somewhere though. Just having an answer without the middle work, I'm not saying you can't do it. I'm just going to question it a little more than I would normally. So that was B. For C, we're going to do everything now. F of x equals negative square root -x, then a +5. So, as a reminder, the order you're supposed to do things, at least as I like to do, is the horizontal shift, because we do shifts first and last, then the horizontal reflections. Horizontal always comes before vertical, so the vertical reflection, then the vertical shift. Is there a horizontal? I'm missing a number. I'm sorry. I forgot my +3 at the end. There is supposed to be a +3 at the end. Make sure you have that in your function. This should be negative square root of -x + 5, then a +3 outside. So is there a horizontal shift? Yes, there is. Horizontal stuff's inside. There's a +5 inside, which means we're shifting left 5. Is there a horizontal reflection? Why, yes, there is a negative in front of the x inside, which means there's a horizontal reflection. You could write yes here, you could write horizontal reflection, whatever you like. Is there a vertical reflection? Well, yes, there is a negative outside of the core function. So yes, there is a vertical reflection. Is there a vertical shift? Remember, vertical stuff's outside. Well, there's that +3 that I almost forgot to write. So there is a vertical shift, and that's up 3. Not down 3, up 3. Horizontals are backwards, verticals are not. So those are the 4 steps we're going to have to do. So I'll do in black the core function, a square root of x, starts at the origin. And then we have that, what we call slow growth to the right, looks like a parabola on its side. Oops. There we go. So that's our core, not x squared, square root of x. For the first step, let's do that in blue. So that'll be the left 5. So left 1, 2, 3, 4, 5. It's -5 over here. So our point is now here at -5, 0, and we're still going to have that same shape. So we'll call that step 1. Then we're going to do a horizontal reflection. Let's do that in orange. Horizontal reflection means left and right. So the y-axis is our mirror. So we're reflecting about that vertical line. So this point that used to be over at -5, 0, it's going to reflect all the way over to 5, 0. 1, 2, 3, 4, 5. We're in orange. So again, this point that was at -5, left 5, is now going to be right 5. Now this graph used to be pointing up and right, but all the right and lefts are reversed now. So instead of pointing right, we'll point left from this point. Just trying to fix that a little bit. There we go. So that's the end of step 2. That's our horizontal reflection. Then for step 3, we're going to do a vertical reflection. Let's do that in lime green. Vertical reflection means up becomes down, down becomes up. So our mirror is the x-axis. And we're just reflecting the orange ghost. So this point was sitting on the x-axis. It's sitting on the mirror, so it's not going to move. So that point stays where it was, but now instead of going left and up, we're going to go left and down. And I'm trying to maintain the appearance of the shape as much as I can each time. I'm doing my best. We can only do so much with our skills. So that was the vertical reflection. And then for the final image, we're going to take that and we're going to shift it up 3. So this point right here that had a height of 0 will go up to a height of 3, and we'll do that in red. So the final step, the answer will be in red, and we'll do this one solid. So this point that had a height of 0 shifts up to a height of 3. So that point right there is 5, 3. Now we're using the green as the ghost image, which was going down and left before. We're not reflecting anything, so this should still be going down and up with that similar shape. Kind of looking like a parabola-ish shape, like that. So that's the end of step 4, which is the answer. So again, if you don't like all this jumbled mess on one page, you can then just take that, start a new graph, and only draw the actual image, which is at the point 5, comma 3, and then going down and left. Again, paper pencil test. I would take just the one with all the different colors on it. This is perfectly fine as long as you illustrate which one is the answer. But I find that a lot of students like to just redraw this and only draw the answer. I think that's a good idea, especially since that's the way your homeworks and tests are going to flow. You're only going to see one single image for your multiple choice answers. So this is one of my favorite problems because it does a little bit of everything. Alrighty. Just as an extra little memo, and I will admit I'm not going to throw a test question on this. I won't say whether there's a homework question or not, but I won't throw a test question on it. But you can probably guess whether there's a homework question or not. Vertical shifts. And sorry, not shifts, vertical stretches and shrinking. There's also horizontal stretching and shrinking, but we're not going to get into that in here. But a vertical stretch or a vertical shrink, this is when you have a number in front of the core. So we've seen things in front of the core so far, but it was just a negative. So a negative meant a vertical reflection. If you have a number in front of the core, that's C, that is going to cause the graph to either grow quicker or to grow slower. Quicker being a stretch, so if your constant is like a 2 or a 3 or a 4 or a 10 or 100, that's going to make this thing hit higher heights quicker, which imagine that if you took the graph and you grabbed it by the top and the bottom and it was made of elastic and you just pulled vertically, that would make the graph, it feels like it goes narrower, but what you're really doing is making the heights go up more and down more. So a vertical stretch, again, is like you grab the top and bottom of a piece of elastic paper, let's say, elastic graph, and you just pulled it as hard as you could. That would cause it to stretch. Whereas shrinking, if the constant is like a half or a quarter or 2/3 or 0.1, imagine that you, instead of pulling them apart vertically, you were just squish them together. And squishing them together would make that graph look a little wider. But what's really happening is that the heights are just growing a lot slower. So again, that's if you have a number outside the core of the function. So I'm just going to really quickly do an example of this. Example 5. For A, we're going to go with f of x is equal to 5x squared. And the 5 is going to cause a vertical stretch. It's going to make this thing grow a lot quicker than it normally would have as just an x squared. 10 would make it grow even quicker. 15 would make it grow even quicker. 17 would make it grow even quicker. So if this is what your x squared graph, that's supposed to be dotted. If this is x squared, 5x squared is going to look more like this. That would be 5x squared. Again, just imagine like you grab the tops and bottoms of the function itself and you just pull them apart from each other. And it would again, it feels like that it squishes in left and right, but the actual squishing effect is caused vertically. Whereas B, let's go with f of x is equal to 1/4 x squared. So this 1/4 is a constant multiplier by the core, and because it's less than 1, this is going to cause a vertical shrink. It grows slower than it would have previously. I'll color. So again, for our x squared graph, which I forgot to put the arrows on the other one, not a huge deal. So that's our basic x squared. With that shrinking factor, it's imagine that we, again, put our hands at the top and bottom of this graph and push them together, like we're flattening it out. So it makes it grow slower, which also makes it feel wider, arguably. It takes a lot longer to hit the same heights as the other one. And if I change this 1/4 to a 1/10, it would make it even wider. If I change it to a 1/100th, it would make it even wider. So that's the effect of a vertical stretch or shrink. Again, I'm not going to test on this. I'll tell you there's a 50% chance there's a homework problem on it, but it's still an important idea to see. I'm not a huge fan of doing stuff that's outside of content, but this really should be content. I don't know why it's not in our course content anymore, technically. So there it is. It's important. You've seen it. And that will actually close out 2.5. All right, 2.6 then. Combos of functions as well as composite functions. Combinations of functions means adding, subtracting, multiplying, and dividing two different functions given two different functions. We'll get into that in a little bit though, because we're going to start out talking about the domains of functions. We talked about domains and ranges of equations when they were graphed, or if we were given like set builder notation with them back in 2.1, I believe. But we did not do the domain of an equation written out as an equation or as a function, either way. And quite honestly, I can't just give you a blanket statement for finding the domain of any random function. We have to do this as a case-by-case scenario. And the three cases that we'll focus on in Math 161 are the same three types of functions that we focus most of our attentions on throughout the course. Polynomials, which are things like x squared plus 5x plus 7. Rationals, which are where you've got those fractions with variables littered all over the tops and bottoms, like x plus 3 over x minus 7. And radicals, which are our square roots, our cube roots, our fourth roots, anything like that. So again, three cases. This is extremely case dependent. And the first case is the easiest one by far. Now remember, what does it mean to be talking about the domain of a function? We're talking about what we can actually plug in, what x values we can use. So if there's an x value that we can't use, then it's not in the domain. In other words, if there's a number that if we were to plug it into the function and it spits out nonsense, maybe an undefined number, maybe an imaginary number, because domain is only for real numbers, no imaginary numbers ever for domain for us. So again, we're looking for numbers that when we plug them into the function, that we actually get values. That means that it's in the domain. If we were to plug a number in for the x and it spits out undefined, does not exist, imaginary numbers, then that is outside of the domain. Now remember, for domains, we're supposed to be using interval notation. So parentheses and brackets, there'll be infinities and negative infinities. You may even see some unions here and there. So our three cases. Polynomials, those things like x squared plus 5x plus 7. The domain of any polynomial is all real numbers. In other words, negative infinity to positive infinity. Because there is no number that you can't plug into a polynomial. X squared plus 5x plus 7. Take the next 7 weeks of your life and try and come up with a number that you plug it in and it spits out nonsense. It doesn't exist. You can plug in 0. You can plug in 1. You can plug in 5.7932. You can plug in negative 10 billion. You can plug in pi. You'll always get an answer. And getting an answer means it's in the domain. So polynomials are super short and easy. They're just a snap of a finger. I don't know if you heard that. I'll try it again. Snap of a finger. The answer is all real numbers. For rational functions, in other words, fraction functions, functions with variables in the denominator, remember there is one and only one number that we are not allowed to divide by. And that number is, drum roll, 0. We can't divide by 0. It makes the world, as we jokingly say, blow up. So what do you do to find the domain? Well, we've actually talked about this before in class, the very beginning of the semester. You set the denominator not equal to 0. You can use the equal symbol. You can use the not equal symbol. I like to use not equals because it reminds me this is what doesn't work. You might get confused otherwise. So we're going to take the denominator and we say this thing is not allowed to be 0. So we set it not equal to 0. We solve that, and boom, we have our domain. In fact, we have the opposite of the domain. So it'll be every number except for usually just 1 or 2 or 3 values. For radicals, it depends on whether we're talking about square roots or cube roots or any other higher indices. It's really just about whether they're even or odd. We can't take square roots of negatives. That spits out imaginary numbers. Domain deals with real numbers only. So we can't take square roots of negatives or fourth roots of negatives. That doesn't spit out an I. It spits out something equally weird, but we won't talk about that. So if you have an even index like a square root or a fourth root, and we usually just do square roots in here, that means, well, the inside of a square root has to be positive or 0. So we set the inside greater than or equal to 0. That will give us all the values in the domain for an even indexed radical. The reason we set the inside bigger than or equal to 0 is because we don't want the inside to become negative. If it becomes negative, imaginary numbers or what other weird version of imaginary numbers there are for fourth and sixth indices come out, and we don't want that. So with the rationals, we're finding what doesn't work. With the radicals, we're finding what does work. Notice I don't say anything about odd indices, and that's because we can take a cube root of a negative, we can take a cube root of a positive, we can take a cube root of 0. If you're talking about cube roots, the domain's everything. If you're talking about fifth roots, the domain's everything. If you're talking about seventh roots, the domain is everything. It's kind of like a polynomial. It's an easy case. Quite honestly, I will not do that on a test. If you get a radical problem in its domain, it's going to be an even index, guaranteed. So let's try out these 3 cases. And we're in a new section. So this is example 1. As a reminder, 2.6 now. Example 1, and we are going to find the domain. In other words, all the values that we can plug into the function. And for A, I got f of x equals 32x to the 9th minus 3.5 x to the 3rd plus pi times x minus 1. That's a fun polynomial. Quite honestly, there's no reason for me to have made these numbers so complicated outside of the fact to prove a point that this problem is super easy no matter what. When you are given a problem that says to find the domain and I give you a function, remember the picture one, you're just seeing how far left and right it goes. This, we don't know how to graph this yet, so we can't really do anything with that. We have to have these 3 cases understood. We have to know whether this is a polynomial, a rational, or a radical. It's not a rational because there's no fraction with variables littered in a bottom. It's not a radical because I don't see any square roots or cube roots. It's a polynomial because these are just constants times x to powers, constants times x to a power, a constant times an x to a power. Yeah, it's decimals and irrational numbers in there, but it doesn't matter. This is a polynomial, which says that the domain is automatically, if you flip back to your notes from previously, all real numbers, negative infinity to infinity. That's the answer. If you were doing this by hand, which you won't be, you could also use the symbol for all real numbers, but that's how it's going to be seen in my math lab homework or test. B, let's do that over here. And we're going to have f of x equals 3x plus 5 over 2x minus 7. How am I doing on time? 5 minutes. All right. So f of x equals, that's 3x plus 5 on the top and 2x minus 7 on the bottom. This is not a polynomial because we see a fraction with variables littered in the bottom. Just one of them, but that's enough to make this what we call rational. Remember, in math, the word rational means fraction. And if you flip back to your cases, this was the second one. And we said fractions, well, that's a division. And there's one number we can't divide by in the world, and that's 0. So anything that makes this bottom 0 is going to make this whole thing explode. It's going to cause it to be undefined, doesn't exist, whatever you like to say. So to account for that, to make sure it doesn't happen, we take the bottom. So I'm going to make this own new little equation. We take the bottom, just the bottom, and we set it not equal to 0. This is us saying the bottom is not allowed to be 0. Again, if you don't use the not equal symbol, as long as you interpret it correctly later, that's fine. But this is us saying we're not allowed to divide by 0, so whatever this equation, whatever the solution of this is, would make the bottom 0, and we have to throw it in the trash. Well, to solve that, we're just going to add 7 to both sides, which will give us 2x, and the not equal symbol operates just the same as an equals, so 2x can't be 7. If we divide both sides by 2, then that's going to tell us that x is not allowed to be 7/2. There is only one number in the entire world that makes this function blow up on itself. If you turn this x into a 7/2 in the bottom, you can do it in the top, it won't matter what the top turns out to be. But if you make this a 7/2, the 2's will cancel, you'll get 7 minus 7, which is 0, and boom, you're dividing by 0, literally boom, problem explodes. So the domain. We're saying that the domain is everything but 7/2. I actually want to draw this one on the number line. Here's 7/2. And we're saying everything works except for this. So in red will be the solution. So all the numbers to the left of 7/2 works. Or works, whatever. All the numbers to the right of 7/2 works. But 7/2 does not. There's a hole here. So you can put a little hole, or you can surround it with parentheses facing the opposite directions. So again, the other version, here's your 7/2. You have a hole at 7/2, and then you're shading to the left forever, and you're shading to the right forever. Sorry that 7/2 looks a little ugly, but it's still the same number. These are the same representations. One just has the appropriate parentheses, one uses an open circle. So with that, it makes it a lot easier to tell what the domain is. It's everything to the left of 7/2. So we got to start at -infinity, comma, and we're going along until we hit 7/2, and we have to skip 7/2. Skipping it means we need a parentheses. But then we got more solution to the right, which means we need a union. And the more solution to the right, it starts at 7/2, and again, a parentheses because it's excluded, and we go right forever to +infinity. Now remember, you have to use interval notation for this stuff. That's how the answers are going to be seen, or that's how they're going to be requested. If you just say x can't be 7/2, that is not acceptable in a test. This is correct, but it's not in the appropriate format. You would not get full credit for that. And in fact, you would get no credit for it on the test because we're doing this electronically. So please understand how these have to be written. We have a minute left, so I'm going to skip C. We will start with C next time. So we did finish 2.5 today. We're about, I don't know, a third of the way through 2.6 roughly. So we'll definitely finish 2.6 next time. We'll do a decent amount of work with 2.7, maybe just a little bit of work, but we're getting near the end of chapter 2. We're coming to a close. But for now, have a good day. Stay safe, everyone. If you have any questions, please email me. Remember, there is a discussion board set up on Canvas. I have not seen any questions or answers up there yet, and that's okay. But remember, you can discuss with each other, and that might be helpful. Besides that, have a good one. We'll see you on the internet. on Thursday.